Looks like we're just about there. Welcome back, everyone, so far. It looks like we have an even split, 2 in person, 2 over Zoom, so it's good to have equal representatives on both sides. And it's official, just about. We can get started. Welcome back, everyone. For today's class, we're going to take any questions that folks might have over the exams. Then we're going to go back into section 3.1, work on some more limits. Although those limits are now defining a derivative, the work we do in section 3.1 turns out to be pretty similar to the work that we did in section 2.4. Again, that's the value of chapter 2. Its whole purpose is to help us evaluate the derivative of a function. In section 3.2 will look into more information about the derivative, geometrically, what it looks like for something to be differentiable by a graph, and other kinds of interesting things along those lines. But 3.3 is when we're going to start computing derivatives in a more fast way without using the limit. We'll see a lot of properties that makes us get through these in a nice, more clean way. But other announcements before we get started is there's a revision on this file right here, the exam 1 formula sheet. And I forget which student pointed this out, but thanks goes out to that student for sure, because the error on the old formula sheet, let's take a look at the new one. This is the one that's actually going to be on the real exam 1. I got this fixed in time. I had 2 sets of limit laws, and that was my intention. I accidentally copied this limit law where we're going to a finite point, A, twice, so it wasn't very helpful. So I put in the limits at infinity. I intended to have this as the first set, and then the other limit laws from section 2.4 as the second set. I have it condensed now to 1 page this time, so it's the same stuff. Well, it's more. This stuff has been included, now just all in 1 page. So that's, again, going to be the real last page of exam 1. And that's what that edit there was all about. But any questions questions or comments at the moment, folks, about the upcoming exam 1 or otherwise? Okay, other things I want to mention are, I did say I was going to post a 3rd quiz on this week, but I had a change of heart on Wednesday when I was about to write it. I felt that if we have an exam coming up on these sections, quiz 2 is already going to be due today, or is due today, then I felt it was going to be a little bit busy to post a 3rd quiz due on a Thursday of this week where we're already doing an exam. So for that reason, I didn't have a 3rd quiz posted there. So for preparation for studying for exam 1, definitely fill out these sections, finish them out in WebAssign. If you need to request an extension, we showed how to do that last class. And if you need some help with that as well, don't hesitate to ask. I'll be happy to take a look at that again. After these are finished off, definitely go and make sure you've got quiz 1, quiz 2 sent in. And when I grade those, even if you turn in a hard copy, I'm going to scan it and send it back to you at your ISU email address, just so you're going to have that available as an extra additional resource for the upcoming exam. But I think that's my whole spiel on the announcements for today. Again, any questions or comments then, folks, before we get started? Okay, well, let's begin where we left off. We're in section 3.1. And this is the diagram that we produced to just get a feel for what do you even mean when you say the derivative of a function. The idea is you have an original function, this is the one in black, and you're interested in a specific point, say A, where the tangent line can be drawn through at that one point. We would love to get the equation of that tangent line. And if we can get it, we'll call the slope of that the derivative of f at A. We write out in this kind of symbol here and just read it out by saying this. So the more important thing about all this, we'll harp on this quite a lot in sections 3.2, 3.3, and so on, is that all the derivative is a slope. Well, slope of the tangent line, there's more information there, but this is the picture of what we're trying to compute each time we do a derivative. Then we made this less abstract by grabbing an actual function. Here's our degree 3 polynomial and showed how to put it into practice. It's all about this limit right here. If we want the tangent line of the curve y equals f of x, That's the f of x function. We need a point, and the first coordinate a right here was given to be 1. That's just the value that goes into the formula right above. So we did the limit as h goes to 0 of f at 1 plus h, 1 coming from here, minus f of 1. It was not an easy limit, but we're going to practice with some more of these just to see how they all go. Due to the power 3 on the function, this is the hardest part right here, I'd say, because if we made any mistake there, no matter how small, there's a good chance these cancellations you see here and here just wouldn't have worked out. And in fact, the only way we're on the right track for computing this limit is if every term, like this one here, that doesn't involve h, it has to cancel out. The need for that cancellation is because we're trying to use direct substitution, which means that h needs to cancel some way somehow, but it will only work if the surviving terms upon cancellation, every single one of them has to have a factor h. That's what allows this cancellation to work. Then up here, it's just direct substitution, and we had a value -2. We didn't say it on these notes, but we're going to start saying this, so we might as well right now. That value -2 can be rephrased by saying f prime at 1, again, 1 came from this point way up here, equals -2. Or if we said this in ordinary words, we would say the derivative of f at a equals 1 is -2. Once we found that value of -2, and it was pretty tricky on this one, lots of algebra, we just go back to the standard equation for a line. This is the so-called point slope equation for the line. Grab the original point, the slope we painstakingly found, and just plug it all in. So this is the process each time we do a tangent line equation. And then down here, this is what we produced. -2x plus 4 is this blue line going this way. Our cubic function looks more impressive than this, but we only have just a small window. But right here, we say that the derivative of f at 2 produces this tangent line, and that tangent line is the best. Let me try again with that. Best local linear because it's a linear equation, local because it only works nearby 1. In fact, if you go even close to 2, we're way off, right? But if you're only concerned about what's happening around 1, this is the best local linear approximation to y equals f of x at a equals 1. And this idea is used quite a lot in applications. Sometimes in physics, for example, there's some physical systems you would like to work on, optics or pendulums, lots of things like that. But these imply differential equations when we try to work on those systems, and differential equations is tough enough as it is. But in physics, as an application to all this, they take something complicated, linearize it, and then do all the solving with the local linear approximation. That gives them very good solutions, as long as you're only concerned about right around 1. If you're concerned around 2, we'll just come up here, change the point to 2 and whatever the second coordinate is, and redo the whole process, and you have the next approximation. But that's visually what we're trying to do in this section so far through this picture. Algebraically, it is tricky, so we're going to take our time when we do the very next ones. But any questions at all, folks, at this second look at this one? Okay, let's try it all over again. So new function, just part B, find an equation of the tangent line to this curve, y equals root x plus 5 at the point -1, 2. Well, the formula is way up there, but sometimes when you're trying to solve these problems and understanding how everything goes, it's a good idea to just try to write down the formula from memory. It's easy to mess up the moment you're learning this, but this kind of forces your brain to really retain this kind of stuff. Sure, on exam 2, I would supply this formula, but the more you are familiar with it, the more about it you can memorize, the easier it is to use on an exam setting. So this is going to be always pretty much my first step. I'm going to use this color just to signify its importance. First thing we want for a tangent line equation is a slope m which is now the limit as h goes to 0, f at a plus h minus f of a, all which is divided by h. So that's our formula to copy down. It's confusing already when you do write this formula, because we need to know what is the function f. It's just this right here. Think of whenever you see a y equals, it's really y equals f of x if you need function notation. And we do because lots of interesting things are defined through function notation. So we would probably just rewrite f of x is root x plus 5. If the problem just gives you f of x equals that, less confusing, but sometimes they change the notation and we have to interpret it this way. Next biggest thing that's confusing about this is to get it going, we need the a value. Anyone spotted what it should be? Is it a -1 or is it a +2? Good call. The a value is always the very first coordinate. The book rewrites this as saying this is a f of a when they go to write out their notation. So it immediately implies, like you said, the -1 right here is the a value. And it also tells us what f of a is. F at -1 has to be +2. And we could check that out. Plug -1 in here, it'd be the root of 4, and it would come out as a +2. That's an interesting observation because sometimes, it's just fast to grab the value out rather than making a silly mistake over here. And then the whole limit would be hard to deconstruct to see what's going wrong. So take advantage of that as a shortcut. And we can now say for our next step, I'm just going to write a long chain of equalities, all of them equal to m. And the next one is limit h goes to 0. We switch out the function f that came from the formula to its actual algebraic expression and just write in root. Well, maybe let me take one more step, just so I'm not taking too many steps at once. Let me just put in -1 plus h in here first, minus f of -1. Then I'll substitute values back in here, so we're not doing a whole bunch of stuff at once. So I didn't do much here. On line 1, I copied down the formula. On line 2, I just substituted in the value for a that was supplied here. Now let's take this whole thing, work it out in the margin. F at -1 plus h would be the square root of, right where we had x, we go -1 plus h plus 5. Parentheses weren't necessary, but it's just my way of saying that -1 plus h went into the spot where x was. So we'll just drop them on the next step. This is square root h plus 4. So that's what's going into that position. We did mention f of -1 should just be the 2. But if you're the skeptical type, it doesn't hurt to check that out. If this was ever incorrect, the whole question would be damaged and it'd be thrown away if it was a real exam. But f at -1, we'll do it mostly just for practice. Plug -1 in here, you get root -1 plus 5, which is the root of 4, which comes out as 2, like we were expecting. Now we're just about done with the substitution part. We're going to throw in these values that we found here and here and see what the limit is really going to come out as. We are dealing with today a limit as h goes to 0 of, across the numerator, follow the color coding for the substitutions on the right, root h plus 4 minus 2, now divide by h. So that's our limit to compute on this one. Any questions, folks, on getting to this step? Okay, well, it's not an easy limit, really. If we look at this carefully, this is a convoluted looking function in the variable h. And if you try to plug h as 0 right in that spot, well, that would be undefined, which doesn't tell us if the limit exists or not. It just tells us 0 is not in domain of that function. We cannot use direct substitution yet. So we have to do something algebraically to this. Sadly, that h is trapped in the root function. It can't interact with this h. So we need something else. Anyone recall how to handle a situation like this? Sorry, say again?
Multiply by that's not
You're on the right track.
the opposite. It's like plus two.
Exactly. We're going for the conjugate, in other words. Exactly. That's what we did way back in section 2.4, but it's just been a while. So the reminder in 2.4 was, if you have a function that looks like, say, this, our algebraic strategy was just a factor, remove the part that gave us the discontinuity, x plus 3, then we're back into direct substitution. But ours looks a little bit more like this one right here. And so just like you said, the strategy is to multiply by the conjugate. So we're pretty much, in a real sense, just redoing part B of example 3. That means at this stage, this is really a review of the exam material from this step down. If this was an exam question, it would start right there, and your job is just to finish out the limit. So let's do that by now, like we were saying, multiply by the conjugate, go times root h plus 4, change the sign like you said to plus 2, root h plus 4 plus 2. Parentheses here are just a reminder visually that I have to FOIL all this out. Well, we get to FOIL all this out. We're all involved in this. So this is limit. H goes to 0. Slightly longer fraction bar. I'll show all the terms, but if you've done this a lot and you did write the two middle terms, because you know there's a cancellation, like we see right here and here, that would always be totally fine. But for the sake of making the notes readable, let me write these in. First, it's this to this. A square root times a square root just gives you the thing inside. People call that the radicand, h plus 4. I always thought that was a weird word. Then multiply here way out to here. That's going to be plus 2 root h plus 4. Then we're done distribution of the root h plus 4. We're now distributing all of this. Multiplies here first, so minus 2. Root h plus 4. Really, we're just putting the coefficient right in front and multiplying this way. And then last one, negative 2 times negative 2 gives us a negative 4. And that settles the entire numerator after FOILing out those two groups. Does that look all right to folks, visualizing that multiplication down to here? Okay, next step is a very common theme when we're dealing with limits, derivatives, just algebra in general. You usually want to expand out the denominator. We use the FOIL method, and you usually do not want to expand out the denominator. We'll see why. The whole reason is we want to cancel that h by the red dot. If you distribute into a group, you can still cancel, but then you need to factor it back out, so we'd have to reverse that work. Best to just leave h right here. Let me try again. There we go. Leave h right here. Multiply it against this next denominator, root h plus 4 plus 2. So if we can navigate through this limit, we're home free. It looks more complicated, but that's just before the cancellations. So the roots in the middle, they'll always cancel because we multiplied by the conjugate here. So that's an expectation. Positive 4, negative 4 cancels. And you can cancel now this h with this h because that's the lone surviving term. I'll show one more step though, because doing too many cancellations on one line makes the notes kind of vague. So last step, just for clarity, you can skip this and cancel if you prefer. Limit h goes to 0 of just the lone h survivor in the numerator. Down below is h times root h plus 4 plus 2. And here's our big cancellation. The reason this process was so long is because we're taking h goes into 0, meaning that 0 here is always out of the domain in the formula for the derivative just by its nature. But the moment you do this, the remaining function, let me put a 1 here because I have that habit of forgetting there's a numerator if I don't put it in. But now the remaining function is continuous when h goes to 0. So this part, h goes to 0 means that h right there goes to 0 as well. So let's write in what's left. We have 1 over root 0 plus 4. Yellow highlighting just showing it came from h goes to 0 in the limiting operator. then plus 2, which means this is 1 over really just a root 4, so 2 plus 2, giving us finally 1/4. And now we started at m, we followed basically like a train tracks of equalities. We have now obtained m is 1/4. Or a fancy way to say all this is the derivative of f. That's how we indicate the derivative of f with those symbolizations at a equals -1, because we were doing a tangent line at that point, -1, 2. We start with the function f of x, but we produce a new function called the derivative of f at x. It gives us the slope of the tangent line at -1, and we found that's 1/4. Writing this in the pencil tool just because this is not completely introduced yet as a symbol. It's just a little bit further down on the notes, but we're close enough to start thinking about using it. Any questions at all, folks, on getting through that whole limit? Okay, well, this is pretty much the wrap-up phase. Once we get the slope of 1/4, we'll go back to the original point, -1, 2, and now we're just using the point slope equation of the line to build out the tangent equation. So I'll say here, tangent line equation is found by taking y minus y1 is a slope m. Let's use that special color again just to connect those thoughts, times x minus x1. So this will be y minus, the y1 value is right up here, the point that was supplied, so my y minus 2 equals slope m, way over here, 1/4, multiplying x minus x1, which is a -1, so watch for the double negation. And that's our tangent line equation. Still have to do stuff to this. Let's simplify this. I write this y minus. We're expecting a denominator of 4, so I'm going to convert this one, the -2, to -8/4. Gets us back to 2 upon simplifying. Will be compatible with that denominator. Then it's 1/4 x. This is a +1, so visualize a 4th multiplying +1, just a positive 1/4. Finally, add 8/4 to both sides. Y is 1/4 x plus 9/4. And we got it, folks. That's our tangent line equation. If we were to plot the original curve, that one way up here, and this one on the same set of axes, we should see, as we zoom in on the point -1, 2 specifically, that the original function and our tangent line equation are now essentially the same curve. It'll be this one, best local linear approximation to that function at the given point. We did that once already when we produced this graph. Let's try it one more time. It's a valuable check, and it's really, honestly, a really great picture to think about every single time you do a tangent line equation, because you need to know, what did you just produce? Not easy to see just by all of this cloud of algebra and calculus. So this is the big punchline to all of this work. Throw in the function up here, f of x equals square root x plus 5. So we've got a function going. We're concerned about the points -1, 2. So right around here is where all the action is. To see if we have the right tangent line equation, go y equals 1/4 x. Slope looks like it could be right on this thing, but it has to move up a certain amount. We said it needs to move upwards by 9/4. So add 9/4. And right there at that point in black is the intersection between the tangent line and the original function f of x. A check on this is not perfect, but this is overwhelming numerical evidence at this point that we did everything right, and that's the right equation. If we want more evidence, just zoom in on this thing, and you should see this happen. The lines are starting to overlap. You can't really distinguish between the two. So it looks like from bounds of -1.4 to +1.6, the difference between the given function, which is complicated as a square root function, is extremely minimal when compared to the tangent line equation. So if we had a more complicated system going on with this, maybe multiple functions like these, we might have to take advantage of linearizations, this kind of process. So at the end of the day, that's our tangent line process. And this part right here was the derivative. But we'll try out a couple more problems along these lines. And at the very end of these notes, we have an honest application that can tell us why we care about tangent line equations. But any last questions, folks, before we try the next one? Okay, let's give this next one a try. In the next set, here's where we finally formally define the f prime at a symbol right here. We'll say the derivative of function f at a number a will always be denoted by f prime of a. And really the only thing new about this formula is we didn't put the slope in here. We're now emphasizing the function, which we'll call the derivative of f. F prime at one point a is through a limit. That's kind of unfortunate in a way when you think about it, because an original function f, like say this one here, every single point on this function implies a slope of a tangent line, which would give you the value of the f prime over here. And so from this function, we're really building a totally rad new function at the same time. So we call that the derivative of f at a, and same limit as before. So what we're going to do now is practice just computing the derivative f, this time at an unknown value a. On the prior problems, a was 1, a was 2 potentially, forgot all the values a was. No, it was a 1 and then a negative 1 for a. But now we're doing this for all values a whatsoever. Let's give this a try and see how it goes. First thing we do is just apply that definition here and write out the derivative of f at a, or f prime of a, equals limit h goes to 0, f at a plus h minus f of a, all of which divided by h. Now this time, our function is a fraction, so we know we're in for it on this one, but it's still going to be good practice. What example 2 is most similar to on problems we've done in the past would be, let's see here, something on this set. Pretty similar to part D. So let's take a look at this just for a moment to get some motivation on what's about to happen on paper. The trouble with part D in section 2.4 limits was we're dealing with fractions once again. The idea is you want your denominators fully factored. So we just factored out a t from this one, leaving t plus 1 behind. Then we just included t plus 1, multiply denominator, numerator on the first fraction, allowing us to put it all together like this. So that's what we're about to do in this problem right here. Only difference is this is a more complicated function. A is an unknown, so the algebra kind of explodes on this one. It looks bad at first, but honestly, this one is a good test of just being confident with algebra and working through problems when they sometimes get really, really long. In calculus, it's occasionally unavoidable. So what we'll do first to organize our work is take a look at f at a plus h. F at a plus h is found by going to these two spots here and here, inserting an a plus h. So we'll go 2, a plus h plus 1. So all you've done is change x to a plus h in the numerator. Down below, a plus h plus 3, and same thing. Anytime I replace a variable with something new, I always put parentheses around it to just direct where that substitution took hold. Now, we should simplify this as much as possible because we're doing stuff to it, right? So any simplifications here makes life a lot easier. This is 2a plus 2h plus 1. No like terms in the numerator. Likewise, no like terms in the denominator, a plus h plus 3. I guess that was not a very big simplification, just achieved distributing 2 through. So that's one part down. Now we look at f of a. But f at a is really the same as f of x. The only thing that happens is we swap out x for a, literally. So in those two positions, just drop in an a. So f of a equals 2a plus 1 divided by a plus 3. And that's going to be dropped in right here. So sometimes the function evaluations like these are a little bit tricky because this is real function composition. Any questions at all, folks, on doing either one? Okay, well, let's now substitute them back into the limit. We're going to need to scroll down a little bit more and see what we get out of this. We have limit h goes to 0. And one thing I want to do with this, because there's so much algebra here, is try to organize it as best as possible to make it easier on your eyes. Easiest mistake is forgetting to copy something down, forgetting to multiply something. And that h is already a bother because the numerator are fractions here and here. This whole thing is now a complex fraction. But here's a strategy. You can take that h. Division by h is equivalent to multiplication by 1 over h. The bracket right here is just the numerator now. Now I'll plug in f of a plus h, which is all of that stuff. So 2a plus 2h plus 1. Put in a long fraction part on that one. Denominator is a plus h plus 3. This minus right here goes to a minus between the fractions. F at a, again, we're basically dropping this in. Let's switch the variable x to a. So 2a plus 1 divide by a plus 3. I'd make that fraction bar a little bit longer as well. So this is the setup, and comparing what we did in the prior section, we're essentially at this stage right here, where we're filling in both denominators, making them identical. Which means we're probably going to want some parentheses around this. Let's put some around here, 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 and here, here, and here. There we go. Now looking at the denominator on the left, a plus h plus 3 is missing a plus 3. So take that value, plug it in here, and here, and the first denominator has been corrected. Then on the next one, this fraction has denominator a plus 3. We already matched up those two, but we're missing that bit, so plug that in, a plus h plus 3. You have to include it numerator and denominator. So there it gets included. And it's good to look at what we did in the past as it relates to this one. This one's more complicated, but really that's all we were doing up here. Once we had the common denominators, we just write it down once, subtract across the numerator, cancel the part that was preventing the limit to go to 0 on this one. We're trying to cancel h, and we should get a value out. Except that our problem is, again, just a little bit more nasty. There is one like this in WebAssign, but I think it's got a slightly nicer configuration in the numerator. So the algebra isn't quite this bad, but this is pretty similar. So here's our next step. Limit h goes to 0. We're going to turn this thing inside the brackets into one whole fraction. So it's going to turn into 1 over h as a fraction, multiplied by that one whole fraction. That should give us enough space. The denominator, we just write in once, a plus h plus 3 times a plus 3. Because we have the least common denominator, we write in once, subtract across the numerator. But as we subtract, we might as well get to the busy work of the distributions. So I want to distribute a plus 3 from the right into the left. I think it's just slightly easier. So starting with a, multiply here. This is the careful step. This is the part at where if you go slower, you're probably going faster. Because if I try to do this at speed, I'm just going to make a mistake. And it's hard to find the mistakes once you make them, when there's so many terms. So go slowly, methodically, and you could save as much as like 10, 15 minutes on a problem like this. It's 2a squared for that one, 2ah for that one. Here to here is just plus a. Let me know if I miss anything on these distributions. It's massively tricky to do that sometimes. Now I'm focusing on the 3 and doing the same kind of distribution. Here to here is plus 6a. Here to here is plus 6h. Here to here is plus a 3. And that finalizes the foiling of the trinomial with the binomial here. It's not exactly FOIL, but similar in spirit. This negative sign causes a major bother. There are some tricks with it, but it's kind of confusing to show on the notes. So just for folks who would like that trick, you could convert this to a plus. I'm going to undo this in a moment. If you did convert it to a plus, you have to distribute -1 into one group or the other, but not both, just one. Probably be good to distribute in here. And now you're multiplying -a into the group, -1 into the group. It saves a step on distribution. But again, it makes my notes totally unreadable. If that's a great shorthand for you that makes sense, I would say go for it. But I'm going to take the extra painful step of really just distributing that negative sign, only for the sake of clarity and carefulness. So negative here goes to a negative here. This parenthesis is going to be the result of FOILing all of that out next. So let's do it again, very carefully and methodically. That's basically all of math. Take 2a times a, 2a squared. 2a times h, that's a plus 2ah. 2a times 3, that's just a plus 6a. With all those distributions done, we move over to the next term. +1 multiplies a. This one's kind of nice. When +1 distributes through, all you're doing is going to copy it a plus h plus 3. So let's write that in. Plus a plus h plus 3. My claim is that's well, almost there. Let's close the parenthesis. That's the result of FOILing out the numerators, maintaining the common denominator. Now we need to distribute the negative sign in and start getting cancellations going. That's a lot of algebra though. Any questions at the moment, folks, to this stage? Or does it look like anything is off or missing? Okay, well, let's keep on proceeding through this. It's now equal to limit. H goes to 0 of, we're multiplying two fractions together. I want to put in the denominator first. And like we mentioned on the last problem, there's no real call to multiply h into any one of these groups. In fact, a plus h plus 3 times a plus 3 just best left in this fully factored form. So I'm just going to write in the whole denominator as h, a plus h plus 3 times a plus 3, and the denominator is resolved. Next, I'm going from here to here, directly copying it in. This is where I make mistakes. It's actually really easy to miscopy something. So go carefully. 2a squared, 2ah plus a plus 6a. We could have combined like terms there, but I'll just keep going. Plus 6h plus 3. Now we're distributing the negative sign. So flip all signs in the group to the right. -1 multiplies here, minus 2a squared, multiplies here, minus 2ah, multiplies here, and so on, minus 6a, minus a. Again, we could have combined those like terms, but let's just keep on going this route. Minus h, and finally, minus 3. Now it's a gigantic mess, but it's progress, folks, because there are a huge amount of cancellations. But first, let's reiterate a comment that we made earlier. It's really helpful for these longer problems. There's a small internal check built into all of this. It goes like this. Every term without a factor h, so the terms without a factor h would be like the -6a or the -3, for example. Every term without a factor h must cancel. Must is always a strong word when we use in this kind of setting, but it's appropriate. The reason for that is we need to cancel that h down there so we can have a continuous function finally and get direct substitution. But if we can't cancel -3, you're not getting rid of that h. So that's where all the fighting is. Let's see if the algebra was done right by forming these cancellations. First, -3 has to have opposite somewhere. There it is at +3. Now we've got a -h, and somewhere here, well, I don't quite, I see some like terms. Maybe let's go with the non-h part. We have a -a, canceling way over here at a +a. Some kind of canceling in random orders. There's also 2a squared here, and a -2a squared. So +2a squared, -2a squared also cancel out. We have a +2ah. It doesn't have to cancel, but this one actually does. Cancels with the -2ah right here. What else do we have? A +6a. That has to go away or else we've made a mistake. But there's a -6a right here. Some weird way, this formula right here is giving us exactly what we want to evaluate this limit. All that's left over is, let me highlight it because it's kind of a mess now. You have a +6h and a -h. Those are the only terms that fail to cancel. So let's combine those terms. It's now limit h goes to 0, smaller fraction bar finally, so just a 5h up above, h times a plus h plus 3 times a plus 3. Now this is the big cancellation. With that gone, finally, we have a continuous function in the variable h. So this h right here goes to 0 in the limit. I'll convey it this way, oftentimes just goes to 0. We copy in just everything that's left, which is 5 over, well, it's a plus 0 plus 3 times a plus 3. Really, we could just call this whole thing a plus 3 squared. Easiest way to type it in, easiest way to write it. That's just because there's two factors of the a plus 3 that emerged. And again, no reason to expand this out, but if you did, it wouldn't hurt. WebAssign will still take the answer. I would take the answer. But you'll find, especially in chapter 4, when we start to do applications with this kind of thing, that's left just in that format. Well, this one was kind of nasty. I did assign one that involves a fraction, so I felt we have to do a fraction too. But any questions at all, folks, on that full process? Okay, these problems are tough, not just because the limit is long. It's tough to say, what in the world did we just produce? Like before, you can think of f prime of a following the big railroad tracks of equalities. We said the derivative of f at a is 5 divided by a plus 3 squared. We want to know, how does that relate to the original function f of x? Let's do another really quick graph to just show what did we actually calculate. So first thing we put in is f of x. It's equal to 2x plus 1 divided by x plus 3. Now we have something else down below here. This is the derivative of f at a. I don't have a great way to put a prime inside of this Desmos calculator, so I'm just going to write it as maybe, how about df, for derivative of f at x equals 5 divided by, well, we use the variable a. Let's match that up. This makes it more compatible looking, a plus 3 squared. Oh, they really don't like that. Let me just change that to a function, let's say f, totally different function. So now here's the big picture of everything we produced so far. The function that we were interested in is this one up here, and that one's plotted in, let me change my tools, green. So we have a green function going this way. But what's interesting is, what is this function in purple trying to say? Well, the easiest way to understand this is take any random point on this graph. Let's say maybe this one right here. If you put a tangent line equation on that graph, the tangent line would look about like that. And it has a slope. The slope of that tangent line, m, well, hard to calculate unless we did that process, but I could tell you m is positive, and m is going to be equal to f prime at a. Looks like this is a value of about maybe a 0.3 that I selected right there. So let's calculate it up here. F at 0.3 is about a 0.4591. Now, looking at the function, the one in purple is the derivative we just calculated. At a 0.3, or right about there, I have a 0.4376. That's pretty close using visual estimation. I didn't know if 0.3 was fully accurate, but that's what this purple curve is doing. Any point on this green line, if you put down a tangent line equation, come up here, that's going to be the actual slope of the tangent line in the second coordinate. So purple is the graph of the derivative, green is the graph of the function. It's a pretty busy plot, but that's why in section 3.2, we're going to look at this a little bit more, seeing how the original function, this one, compares against its derivative here. But I felt like for the very first derivative we calculated, here's f prime of a, I had to use capital F of a. We ought to at least look at a visualization before moving on to the next concepts. Well, any questions at all, folks, on getting through this problem here or the visualization on the right? Okay, well, these are fun enough. Let's try out another one. They're not all going to be this bad. That's one thing we should definitely mention. But the next one, you know, it's a square root function. It's going to be one of those conjugate tricks again. So let's try this out. And kind of the goal for the problems I did write on these notes is the problems that you do on WebAssign, you should be able to go back to this document and kind of match up similar problems. If you find one in WebAssign that just doesn't match up, please don't hesitate to just ask about it, either in class, office hours, before class, after class, or even at the very start of class when I call for questions. I'm looking for that kind of stuff. Anything that seems weird on WebAssign would be an excellent question to start us out. But speaking of things weird, let's calculate another derivative, f prime of a, based off this function here. First step we need to take is say what we're calculating. F prime of a equals, so now that's done. Second step I would take is write down the formula for the derivative. Try to do it cold without looking up at the notes. Again, you'll make mistakes and it's normal, but you'll start to realize the more you try this out, you're nailing it more and more each and every time. That means it's just sort of sinking into your head. When you go to have to use this in an exam setting, it'll be a lot easier. So limit h goes to 0, f at a plus h. Having some trouble with my h's. There we go. Minus f of a. All divide by h. So that's our formula. We don't have an a value. We're not going for a tangent line equation. We're going for the total derivative. We want to know the slope at every single point in the domain of this function, in other words. And by the way, when we think about this one does have a domain that goes like this. To calculate the domain, take what's inside the function, x minus 8. We're only dealing with non-negative values inside of our square root, since we're just doing calculus with real numbers. So we assert that that has to be greater than or equal to 0. So no complex value stuff. Add 8 to both sides. X is greater than or equal to 8. So that tells us our domain is bracket 8 to infinity on this thing. So that's all the valid points for x. Now we'll calculate this derivative right here and take a look at the derivative again. Sometimes something can change on your domain, not always, but on this one it will. So let's go and put in our next steps. F at a plus h. It's just putting an a plus h right there. Let's write it in just for the sake of practicing that. F at a plus h is the square root. I'll not put in the parentheses this time, since really we would just have to write it again without the parentheses. So I'll just drop it in that way this time. Then minus f of a, same exact thing, just simpler looking. We go f of a equals root a minus 8. So that takes care of both these two values here. We're going to substitute them in, and then we're probably expecting the conjugate. We'll definitely use that and hope for the best. So limit h goes to 0. This time the numerator is not as complicated, so I'm going to keep h right where it is. Just drop it in this spot. f at a plus h by substitution is the root a plus h minus 8 minus, next in green, we have root a minus 8. Now we've got our entire formula up here filled in. We just need to evaluate the limit. It's another conjugate. This time it's 2 square roots in our conjugate that we're going to use, but it goes the same exact way. Write out the numerator essentially the same with a positive by that red dot. So root a plus h minus 8 plus root a minus 8. Divide over the same exact quantity. We're just multiplying by a weird looking number 1. A plus h minus 8 plus root a minus 8. And then finally, lim h goes to 0. I'll write out a big fraction bar because I'll write down all terms. But if you didn't write in the middle terms like we mentioned before, always totally fine. But we've only done this a few times, so here's the full visualization. We're distributing here to start, but that's the same root multiplying the same root, so we just copy in the radicand, a plus h minus 8. Next multiplication, here way out to here, it looks kind of abstract, but it's just literally that root in blue multiplying by that root in black. I'll just put them together and write plus root a plus h minus 8 times root a minus 8. We could put them together, but I think it's better to just leave them in this factored form, multiplied like that, because they're just going to cancel anyways. No worries doing more algebra on it. That's the first level of distributions. Next one, we just have to be mindful that when we distribute this term, the negative is going in. And I kind of forgot to put these parentheses in. I like putting those parentheses in just because it feels more natural. You're multiplying one binomial against another. So that's a good inclusion, but not mandatory. So now this multiplication here becomes negative root a minus h times root a plus h minus 8. And last one, here to here, this is actually a tricky multiplication. We need to be careful with this one. What's tricky is that leading negative sign gets written in. Then root a plus h multiplies root a plus, so let me try again. Root a minus 8 multiplies the root of a minus 8. It leaves a minus 8, but we need an extra set of parentheses because that negative sign has to be allowed to distribute through. For me, when I practice a problem like this, this is the most likely spot I would make a mistake right here. Okay, that's the whole numerator. Same thing that we've been doing all along with the denominator. Multiply them together, but don't distribute. So just h times root a plus h minus 8 plus root a minus 8. So there it is in its full glory. Now we start canceling the stuff. But any questions at the moment to that step? Okay, well, we expected that this and this had to cancel out. But you know what? I forgot that I do want to distribute this through. Sometimes when people are doing cancellations, they do a couple things at once. You know, the negative a would multiply this, making it a negative a, canceling the positive a here. This negative distributes through, making it a positive 8, canceling the negative 8. So some people would do the cancellation right at that step. That's always totally allowed. But like we've been mentioning a lot of times, makes the notes almost unreadable. So I'm going to take, for the sake of the notes only, this additional step. Copy in the survivors, a plus h minus 8. Way over here, distribute the negative sign in, minus a plus 8. The downside of this is it's a little bit more writing, but at least we're being extremely clear. Root a plus h minus 8 plus root a minus 8. So with that cancellation out of the way, well, that's a distribution rather. We can easily cancel the negative a, positive a, negative 8, positive 8. And more importantly, it finally tells us that that h right up here can allow the cancellation with that h in that spot. That h by the red dot is the whole reason we had to multiply by the conjugate. It's because we're taking the limit as h goes to 0. So new cancellation. That h is gone. That h is gone. This implies a new cancellation. It's now by, let me put in my 1 up here, just a personal reminder. We now have a continuous function, 1 over all this stuff in the variable h. Direct substitution says that part goes to 0. I usually draw that little arrow going to 0 just to convey it's going to 0 because of the limit. And finally, just write in what survives. 1 over, we're dropping the limit statement because we just used direct substitution. Denominator here is root a minus 8 plus root a minus 8. And those combined, we have like terms down below. The whole derivative of f at a, which we started with way over here in the corner, is 2 root a minus 8. Which means we did it, folks. That's finally the derivative of this function f. Kind of a strange derivative, but any questions at all? Getting down to there. Okay, well, now that we're at this spot, notice that the original function had a domain from 8, including 8, that's why we throw a bracket on it, going off to infinity. But down here, this domain has changed. This is kind of a surprise. Doesn't happen every time with derivatives, but it can happen. This one has domain figured by doing the following. We still take what's inside the root, and we want it to be non-negative, but this time we also want it to be non-zero because you can't put 8 down in there. You divide by 0 once again. It's undefined. So we have to take a minus 8, set it strictly greater than 0 this time, solve, and we have 8 strictly greater than 8. So the domain of f prime, the derivative, is parenthesis 8 off to infinity, whereas the domain of the original function included one additional point. It's actually defined at 8. It would just be 0. I'm not going to ask too many questions about domains when it comes to these, but I did notice in 3.1, a couple of problems does ask about domains. So it'd just be a matter of doing this kind of stuff when it comes up. If you have any questions with the domains, if it seems a little bit weird on those problems, don't hesitate to hit the Ask My Instructor button. It wasn't meant to be the main concept, but turns out I can't delete the domain part of a problem from my side of the axis. So any questions about domain, I would just help you out on that. I wouldn't make that a hard part of the problem. But any last questions, folks, on getting through that limit there? Okay, well, we've done several derivatives so far, several tangent line equations. But one thing we haven't really said so far is, how does this apply to us, like in the real physical world, for example? All of this has been like just kind of a mathematical exercise. So down below, this is our next problem to show what a decent application is of this. Really, there's a plethora of applications. Think about anything in the physical sciences, biology, chemistry, physics, engineering. All of them are going to use derivatives. Later on, they'll be using integrals. And so somehow, some way, all that information is about the slope of the tangent line. So we say the derivative of f at a is the slope right here through the limit statement. But if it's a slope to the tangent line, you can also think of it as the instantaneous rate of change of y equals f of x with respect to x when x is a. That's a fine statement, but I think that's still kind of foggy unless you draw something out. So keep that thought in your mind. The derivative of f at a is the instantaneous rate of change. Let's go way back to the top of the notes. And let's suppose that there was actual units on these axes. Let's say that this was time. So t for time, it may be hours. And let's say the vertical axis going this way is distance, meters or maybe miles. pick your favorite distance unit. So if this was a hours and distance graph, and this was the plot of your distance from a starting point at t hours, the tangent line equation is then really, really interesting. Imagine you're driving a car and this graph is relevant rather. The slope m then turns into instantaneous rate of change. Which would be miles per hour. So if you're driving a car looking at your speedometer readout, that's pretty much what's happening each and every time. If we produced a data chart of your distance from a starting point at a certain time and plot out this curve, find a tangent line at any point, we're just reproducing what your speedometer readout was at that time. So that's one tie into derivatives. Think about speeds, and that's a great way to think about it. But it could really be anything in the physical sciences. So we're going to have a wide selection of applications when we get into chapter 4, applying the derivative. But for the moment, this is a great way to think about it. As you're driving your car, think about a derivative that's always in the background. And it's kind of the idea what's going on down here. But that's this application down below. The application says, if a rock is thrown upwards on the planet Mars, I don't know why we're going to Mars, but it seems like what we're doing today. So you're on Mars, you have a rock, you're throwing it upwards, but when you think about throwing that rock, you have a trajectory that's going like this. This is the person crudely drawn. I'm not a great artist. You throw it, it comes up and around. Or maybe you threw it this way, and which means it's going to come directly back down and you've got to move. Either graph is relevant because when we go to track our displacement, S function right here, we're only going in one dimension. We're only tracking the vertical change of the rock that was thrown up. We're not trying to worry about the horizontal change or any kind of things like that. So people have taken a lot of physics. We're not doing any of the kind of kinematic equations. We're just reducing it down to one dimension and seeing what's happening in that dimension. We need more physics to get a little bit more involved, but this is always a great start to think about what the physicists are eventually going after with their kinematic equations. So let's read through this. It says, it's thrown upward with a velocity of 10 meters per second. So that's just how fast it was going the instant it left your hand. Its height in meters after t seconds is given by the position function s. Sometimes the position function s is referred to as displacement, which we mean is displacement from a starting position. So the starting position would be the height once it was released, and then the displacement is where it is any moment of time after it was thrown. So it's often written down as S. I think we're inheriting this from physics. They often use this as displacement. In the formula, we need a function f, so it's just been rewritten. F of t is that. And that's our equation of motion for the rock throwing upwards. What we want is velocity of the rock after 1 second, but that's just the instantaneous rate of change of the rock at 1 second. That means we're just calculating a derivative at time equals 1. But in this context, if s is displacement, and we take the derivative of s, which is what we're about to do using the definition of the derivative, we go down to a new function v, which would be called velocity. And that's what we want right here when they are asking for the velocity. Let's write down one more because it's going to eventually come up. So v is the derivative of your position function. But if you take this function, it's a function in its own right on the variable t, differentiate that again, you get a, acceleration. And you can keep on differentiating these things. The next one that sometimes gets mentioned, we won't use assimilation a lot, but if you're curious, differentiate the acceleration function again, you get a new function j, which is called the jerk function. And I think the thought about this is, imagine you're building a roller coaster ride, something like this. We want to analyze the displacement of the rider at any part of that track. You also want to know the velocity. You want to make sure it's fun. You need to pay special attention to acceleration because you don't want to hurt anybody. You don't want to say, give someone a 6Gs ride for 10 seconds. That's probably not going to be very helpful for their health. And you need to look at the jerk function, which is the derivative of acceleration, because if that's non-zero, this is probably going to be maybe even a deadly ride. So when we model these kinds of things, roller coasters being an example, these have very, very special considerations taken into place. And they're all related, like we mentioned, in this way. Here to here, here to here, and here to here is just the derivative. All right, derivative as DER, since I didn't really think that through for a shorthand, but you're just taking multiple derivatives to get down from one function to the next. So finally, we'll see these kinds of things come up. In fact, we'll find out how to go from acceleration and go backwards, finding the displacement. But for the moment, all we want is velocity of the rock at 1 second. Because it said 1 second, we were plugging one right here. But this then turns into just this once again. We're taking the limit as h goes to 0 of the function f at 1 plus h. So I plugged the 1 up here as well, coming from the 1 second, only because there was a 1 here, minus f at 1, divide by h. So if we can do this limit right here, we have a velocity function. And if you were so inclined, you could just keep on doing this over and over again, but you would have to do it with a variable a to come up with the acceleration and the jerk functions. So we'll leave that out for when we're further into chapter 3 to see how all those relate. But for the moment, let's do the standard kind of thing and just work these out. F at 1 plus h means we're putting a 1 plus h here and here. That's a good one to do on the margin. That's a good amount of algebra. F at 1 plus h is 10 times 1 plus h minus 1.86 times 1 plus h. And that's a squared. So working through this, we can distribute our 10 through. 10 plus 10h minus 1.86. Let's FOIL this one out. When we FOIL out a perfect square polynomial, like the one by the red dot, we get 1 plus 2h plus h squared. So that's just writing out 1 plus h twice. And this is the pattern each time you square out a polynomial like that. And keeps on going. Let's rewrite this as 10 plus 10h. I'll distribute this through. So negative 1.86 times 1 just gives us negative 1.86. I need negative 1.86 times 2. So let me cheat a little bit here. So negative 3.72 when we distribute here to here. So negative 3.72h. Then finally, negative 1.86 times h squared gives us negative 1.86 h squared. Barely fit into the margin there. So that's our first one, f at 1 plus h. Does that look right to folks so far? Okay, next strategy here is just evaluate f at 1. They never gave us a coordinate. They just gave us 1 second. So this time we really have to calculate this, but not so bad. We're just doing an ordinary function evaluation. Plug 1 here and here, and we'll get the result. So this turns into f at 1, which is equal to just 10 times 1 minus 1.86 times 1 squared. That's just a 10 minus 1.86 altogether. Again, let's treat ourselves to a nice calculator. 10 minus 1.86 gives us an 8.14. And so that's what's going to be plugged in right up here. Okay, we've got all of our computations on the margin ready to go. Now for our next strategy, we just plug it in. Again, I'm gonna let these equality symbols just be a long train track, basically corresponding to the thing we want to find, velocity at 1 second. But now velocity at 1 second is a limit as h goes to 0 of, copy in this part right here, which is all of this stuff, 10 plus 10h minus 1.86 minus 3.72h minus 1.86h squared. There it is. Now that minus sign just comes from right here. Drop in f of 1, that was at 8.14. Slightly longer fraction bar. Let me try again on that. It's kind of hard actually. There we go. Let me put in a fast border as well. So now for the left-hand side, all we have down below is h. And our hope of hopes is every term without h, it had better cancel. So we have 10 minus 1.86. We did that once already. 10 minus 1.86 down here got us at 8.14. So that tells us this plus this is 8.14 minus 8.14, full cancellation on all constants. That's kind of nice. And we have more like terms, 10h minus 3.72h. Let me cheat again. So 6.28h when we combine these two down here. And that gets us to our next statement. Limit h goes to 0. I've already forgot the number. Let me try again. 6.28h, combining this part with this part right here. And then finally, minus 1.86 h squared, all divided by h. Now, you can cancel h here if you like, but usually I like to write out this step. It's a little bit more careful, but it's not required. If you're comfortable canceling h on this step, it's totally fine as well. Factoring out h, though, gives us a 6.28 minus 1.86 h, all of which is divided by h. And this is the point at which we can declare success. We have canceled off this h and this h, puts direct substitution of h going to 0 back on the table. And that's just going to wipe out that term right there. So negative 1.86h is gone. This little statement is just saying converges to 0 in the limit. We're left with just 6.28. But the units for this one, recall it's a slope. It's going to be first the meters from the displacement divided by the seconds per time. Because it's positive, this tells us that 1 second is still traveling upwards at 6.28 meters per second. So that means moving up. If we did velocity maybe at 3 seconds, we'd have to double check. But velocity at 3 seconds, that might be a negative value, which would mean it's going down at whatever the rate was. But that's an instantaneous rate of change. Think of this as like a speedometer on the rock at every single instance of time. That's changing due to the effects of acceleration due to gravity on planet Mars. So we did it, folks. This is the application that goes along with all this kind of stuff. We'll look at a lot of applications in chapter 4, but we'll try to spend some time on them even in chapter 3, because, you know, this kind of stuff is very abstract looking unless we have some kind of tie-in, some picture in our back of our mind on what it all is trying to say. But any last questions at all, folks, navigating through that final limit there? Okay, well, that's all I have for folks today. If you have any other questions, feel free to stick around. I'll be happy to help. Otherwise, I'll see you all when we do our exam on Monday's class. Also, keep in mind, I'm going to be highly available by email, so don't hesitate to write. I'll be responding even on the weekend. Take care, folks. Have a great weekend, and I'll see you all next week. Oh, by the way, week 4 is over, so you're 25% done of the whole semester as well. Congratulations. We're getting there.